Ladies and gentlemen, class recording has begun. So, tomorrow is your test over circular motion, centripetal force, and all things related. This goes back to approximately 2 weeks. We started it on March 6th, on March 4th, where we introduced the idea of centripetal force and circular motion and what's going on with circular motion, how things go in a circle, and those things like that. On March 6th, which was a Wednesday, we spent the day doing problems in class, more conceptual problems in class, off of the first problem set that I gave to you, which looks like this. It's an intro to centripetal acceleration and centripetal force. We spent a day doing text polling that day, and I recorded class that day, and it was a lot of conceptual things on that day related to circular motion, like when things go in a circle, are they accelerating? And if they're accelerating, they have to have a force, and where that force is, and where it comes from, and how big is it, and all those fun things. Okay? So that was the beginning part that we did. The next part, we spent the 2 days doing the circular motion stopper lab, where you had to calculate some circular motion, measure some circular motion, calculate some centripetal force, etc., etc., etc. And then last week, we got into the problems dealing with this unit. Those problems looking at that centripetal force has to come from somewhere. Where does it come from? And then if we know where it comes from, how much of it do we need? We went over 3 kinds of problems last week. The first one dealt with friction acting as centripetal force, and using the coefficient of friction to determine how much frictional force there is, and then taking that and seeing as how fast we can go. The second type of problem we talked about was dealt with the banked curve, where now we have an object that's trying to go straight, but because the road is banked, because it's tilted, there is something that actually gets in the way of that object and prevents it from going straight. And then the third kind of problem that we talked about was the vertical circle, where now an object is going in a circle up and down, and gravity will change the effect that the other forces have to have on that object. Things like normal force, things like tension, depending on where we are in the motion of the path of that motion, and relating to is gravity helping the centripetal force by pointing towards the middle, or is gravity hurting the centripetal force by pointing away from the middle? Okay? So that was a quick rundown. As far as the test goes, I think the test is going to be 14 multiple choice questions, and then it is going to be 3 problems. Each of the problems is worth 8 points apiece. That's 24 there, it's 14 for the questions. Takes us to 38 points total, which is a little bit about the same as the last test, but a little bit more heavy on the problem side than it is on the multiple choice side. Okay. Questions? Do you guys have any questions related to the test, or you want me to talk about some things, or you guys have anything specific that you want to talk about? No.
How was your week?
How was your week?
How many types of problems?
We've basically done 3 types of problems, Emily, and there were the three sheets that I gave you last week. So one is friction as centripetal force, one is bank turn as centripetal force, and the other one is vertical circle path. Okay, and so if there's 3 problems on the test, you probably can figure out what the 3 problems are going to look like. Now, so and with something, this goes for everybody, not just you, but on those sheets, we did a couple of examples from each sheet, but there are other examples on those sheets that, relate to the bank turn or relate to friction, but we didn't do them in class. The answers for all of those problem sets are posted online. So if you check last week, you'll see all the answers to all of those problem sets that I gave you last week on the problems. If you take a look at March 6th, you'll see that there are answers to the original problem set that go along with the class recording where we went over concepts. Okay. Good there? Okay. I mean, weekend was good. It was pretty busy, but
Really?
yeah.
Did you have a great St. Patrick's Day?
No, didn't really do anything real exciting for St. Patrick's Day.
Corned beef at least?
We did have corned beef and cabbage for dinner. Yeah, so but didn't parade or anything like that. Actually, lives in Hinckley or close to Hinckley, and so she always has like a buzzard day kind of thing. So we had that yesterday morning, and you know.
Are they back yet?
We actually did see a few. So did see a few floating around. So she always has like a breakfast, and you know, it's always the same thing every year, but it's pretty good. So you know.
So it must not be sausage gravy.
What?
It must not be sausage gravy.
I mean, there's this. She makes this one thing. It's like sausage plus potatoes plus like green onions and some other things, but it's like kind of an gravy-ish sort of thing. It's pretty good. It's really good. All right. Other questions, either related to my weekend or not.
Can we go over some conceptual?
Sure. Let's go over some conceptual things. All right. So, some conceptual things. From this problem set that I gave you, I believe on the Wednesday, March 6th, so the Wednesday of the first week. The first side of this page all deals with the concept of circular motion. So, questions that we've kind of covered about 100 times. Is an object moving in a circular path accelerating?
Yep.
Yes. That means if it's accelerating, it has to have what? It has to have a net force, and that net force has to point towards where? Center of rotation. Okay, and we call that net force what? Centripetal force. Okay, and then we talked about that the amount of centripetal force depends on a couple of factors. It depends on the mass of the object that is going around in the circle. It depends on the tangential speed of the object, and it depends on the radius of the circle that that object is going around. And we said that those three things all come together in this equation, right? mv squared over r, right? That's how much force is required in order to make an object go around in a circular path. Okay? Good there? We also discussed that, we actually did this in reverse order. We did what I'm about to show you first, but if you know there's an object that has a force on it, Newton's second law tells us that that force is proportional to the mass of the object times its acceleration, right? So, taking apart this equation right here, right? Here's the mass, right? Not yellow. Here's the mass, and that leaves v squared over r left over, right? So we said that that is the centripetal acceleration, right? Depending on how fast the object's going and the radius of the turn. Okay? Taking it back to this problem set, question number 1 asks you about some basics, but then part C says, does the acceleration of the car change? Why or why not? So the answer to that question is, well, it depends. It depends on our frame of reference. We said that the acceleration, along with the force, always have to point where? Towards the center. So, if we just look at an xy axis, the acceleration on one side of the circle points towards the left, or in the positive direction, but then on the other side of the circle, it would point towards the right, in the other direction, right? Technically, those are different accelerations, because why? They're different directions. But later on in the unit, when we were talking about the vertical circle, we said sometimes it's more convenient for us to think about the frame of reference being into the circle or out of the circle. Does that sound familiar from last week? Okay. So if you look at it that way, centripetal acceleration always points towards the middle and never out of the middle. So yeah, I'm probably not going to ask you that question on the test because it's kind of confusing depending on what you look at for your frame of reference. Good there? Mark, go ahead.
For the vertical ones,
Yeah.
like, are you going to give us like a point like on either side, like not just up and down?
No, Mark, I'm either going to give you, so, Mark, we're talking about a vertical circle. I'm only going to give you 1 and 2 points, all right? I'm either going to give you the very, very top or the very, very bottom, okay? Because at that point, we don't have to worry about components on gravity, right? So yeah, I'm either going to give you the very, very top or the very, very bottom.
Yeah, so
Yeah, so, and then yeah, those will be your only 2 options as far as the vertical circle goes. Okay. Any other questions? We good? Okay. Let's take a look at, just from another conceptual question standpoint, station is being designed to be used as a space colony.
That's a space station.
Yeah. I mean, it looks kind of like a tire, but when you put stars around it, space
Those are
station,
stars.
you know? And it's got windows. You know, those are windows.
Space station's missing a few buttons.
So,
That was like a wheel or something.
but you put stars around it, now it's a space station. So. Alright, so it says, the engineers want the inhabitants to experience a centripetal acceleration equal to the acceleration of gravity here on Earth. The space station has a diameter of 8 kilometers. So, first thing, it says, what must be the tangential speed? Okay? So, two things. Earlier on in this unit, and especially during your lab, we talked about a way to calculate tangential speed. What did we say was a way that we could calculate tangential speed? There's one way that you can do it. Well, if it's speed, what do you have to know? Well, more generally, you have to know a displacement or a distance and a time, right? So, Evan, the displacement in this case, or the distance, would be equal to what?
3 pi r.
That's an easy distance for us to know. That's the circumference of the circle, right? Then, if you take that and divide it by something that we call capital T, the period, which is the time for one revolution, you can use this to calculate the tangential speed, right? Do we have enough information to figure that problem out? We got an R, right? Or we can use that to figure out the R, right? But we don't have the time. Okay? But we do have another equation that has tangential speed in it. It looks like this. V squared over R.
Do you have to memorize the 2 pi r over t, or will you give us that?
I mean, you can put it on your note card.
I
You
mean,
know,
you could, but if you give us that, we don't have it.
I'll give you anything on your test.
Well, I mean,
There.
it's not up there.
That's true. That's more of a hey, figure this out, like, because it's like speed, you know, meters per second.
Yeah, okay.
And we did it like
Alright, fine.
100 times on your lab too. So no, that will not be up on the that will not be up on the board. So we can also do this though. This one has tangential speed in it right here, right? So if we can solve this equation, the important thing being here, okay, what is the acceleration? What do they, in the problem, what do they want the acceleration to be here? They want this to be 9.81. So to do that, you can figure out what the tangential speed is. Okay. Is that good there?
So then is centripetal acceleration the same as regular acceleration?
In this case, it is, Rachel, but it doesn't always have to be. Okay? So, let's calculate this, and then we'll go into that, because that leads us into another topic that we discuss next week. Or, sorry, last week. So, did anybody run this through a calculator real quick?
Why is it 4,000?
Because it says that it has a diameter of 8 kilometers.
Pretty sure.
So you
But-
divide by 2.
So you divide by 2 to get the radius, right? And then you don't want kilometers, you want meters, and so
39,240. Oh,
take the square root.
198.090888.
How about if we go with that?
We can go with that, yes.
So that would be the tangential speed that this space station would have to go in order to give us an acceleration equal to 9.81. Okay? Is that good there? Now, let's talk about this a little bit more, because it leads us into a good topic that we started discussing at the end of last week in relation to the vertical circle. Alright, so here's our space station. Let's make it a little bigger. And we've already established that it's going to spin around. We'll make it spin this way. Okay? And there's a person standing in this space station. Let's make him yellow. And there he is.
A very big person.
Yeah, not to scale. All right. Let's not make him yellow. Let's make him red. So here he is, standing on the outside edge of the space station. Circular motion tells us, what is this person standing on the outside edge of the space station trying to do?
Go in a straight line.
Okay. This is what's trying to happen. Can that person go in the straight line, though? They can't. Why not? The wall gets in the way, right? And that wall has to apply a force in which direction? And we call that force centripetal force. But, as we've discussed, centripetal force doesn't come from nowhere. It has to come from something. What do we call a force that comes from a wall? Or a floor? Or a seat? Okay? This is a normal force. Okay? If I did this, oh, out of your keyboard. And I just drew a picture of this object standing here along the floor, and I drew a force pointing upwards like this. You would label that as normal force, yes? Okay? Still normal force here as well. Okay? Now, the one thing that's missing from this picture, though, that we generally have is what? Generally, we have gravity. But in this picture, is there gravity? Not at least in this isolated situation. Okay? Remember last week when we started talking about g-forces and stuff like that? Okay, towards the end of last week? Okay? And we said that g-forces have the ability to make your body appear that it weighs more than it actually does. Does that sound familiar? What, say again? No, this is the same, except now we would apply it a little bit different. Are there g-forces acting on you right now? Yes. A g-force is just a fancy name for a normal force. Is there a normal force acting on you right now? There is. How big is that normal force? 9.81 times your mass, right? It's just equal to the force of gravity. And that makes you feel a certain way. It makes you feel like you. But we talked about, like, on the elevator, if you mess around with your normal force, that can sort of change the sensation of what you feel like, right? So this normal force we refer to as your apparent weight. Okay? Right now, your apparent weight is just equal to whatever gravity is acting on you. But that doesn't come because gravity is acting on you. It comes because you have a normal force acting on you. Okay? So Rachel, going back to your question, could we spin this space station in a way where this normal force would just be equal, or at least in number, to what the force of gravity usually is on us?
Yeah.
Yeah, we could. What would that feel like?
If it was the same as gravity?
If it was the same, if it was equal to m times g. To you, that would just feel like this. It would feel just like you feel right now. Okay? Is there gravity acting on you? No, but your apparent weight is such that it gives you the sensation that it's just the same as you here on Earth. As we said, your apparent weight, what you feel like, doesn't come from gravity, it actually comes from the normal force. Can you have normal force without gravity? In certain instances, yeah. Okay? You ever see like a science fiction movie where they have a space station and it's like spinning around like this to create artificial gravity? Come on, nobody?
Yeah.
Anybody ever see 2001 Space Odyssey?
Would
Really-
it spin
really should.
vertically or would it spin horizontally? That makes me think of a hamster wheel.
Doesn't matter. The hamster wheel, so, Rachel, that's a good question. The hamster, if you think of it as a hamster wheel, that's fine. But there's one problem with you thinking of it as a hamster wheel. On Earth, you have to contend with what? Gravity. So at the top of the hamster wheel, gravity's pulling you down along with the normal force. But if we're out far away from a large gravitational source, the gravity doesn't mean anything. Does that make sense?
Yeah, I'm just trying to think of that as a space station.
Okay. I know.
Does it make sense?
So, but are you okay with that at this point?
Yeah.
Okay. So here, right, as this thing spins around, there is a normal force acting on you that is equal to the centripetal force. We could make that spin in a way that your normal force is just equal to whatever the gravitational force here on Earth would be like. Yeah? Does that make sense?
Yeah.
Okay, so now, let's change it up a little bit. Here's you in an airplane. Whoosh lines, right, going that way. Okay. There. Is that better? Okay. So there's you in an airplane. Does gravity act on you when you're in an airplane? Sure. So you got gravity here, okay? But as you sit there in your seat, right, what else is acting on you? The seat, right? Normal force, okay? And if you're at cruising altitude, not when you're going up or coming down, because obviously those things are a little different, right? But if you're at cruising altitude, what would we say about red and green? They're the same, right? When you're flying on the plane, you basically feel the same as you do just sitting in the seat at home, right? Okay? Unless you have turbulence and stuff like that, obviously that's a little different, okay? But if it's a nice smooth ride, I mean, people do things on an airplane just the same that they do sitting in their, chair at home. It's a little less space usually, and there's some guy next to you that's annoying and talking to you. But other than that, it looks like this. Okay? Now, let's say we take this. Okay? Oh, let's take this. First, let's group these together. And now let's go this way. Okay? Oh, sorry. Here. If it's straight, what's your apparent weight in this situation? It's the same. Same as what you do just sitting at home, right? Okay. All right. Now let's go here. Okay. First, let's ungroup because I gotta mess some things around. Okay. All right. Will gravity still be acting on you in this situation? Yes. Except now, it looks like this. Will normal force be acting on you in this situation? Maybe from the seat in front of you. But if there was a plane that had no seats in it,
Well, which part?
there are. You want to watch that?
Would the pilot have a seat?
Yeah, the pilot has a seat. Yeah. Okay. Okay. No. So, I just moved it out of the picture. Because, Katie, the normal force comes from where? Perpendicular to the object, right? To the surface. Is there a surface here now? No. Does that make sense? So is there a normal force? There is not. Okay? Yeah, I just moved this out of the picture over here. Let's get rid of it. Okay? But what is the plane still doing? The plane is still going down. So now you're going down, and the plane is going down. Do you get any closer to the front of the plane?
Until the plane crashed in the ground.
Not until the plane crashes in the ground, or the plane changes its path, right? If you're falling downward and the plane is falling downward, right? There's no normal force. You're not moving in relation to the plane. This still acting on you? Yes. But what isn't acting on you anymore? So what's your apparent weight? Your apparent weight is 0.
So is apparent weight going to be on the test?
This, Rachel, that gets into, like when we did the vertical circle, what does the pilot feel like at the bottom of his circle versus the top of his circle? Does that make sense? Because if this plane now, okay, let's say this plane, well, the wing isn't attached to it, but okay, now the plane starts pulling out like this, okay, because it doesn't want to crash into the ground, it wants to go back up in the air, right? As it goes down here, gravity is still acting on it, right? When it gets to the very, very bottom, right, gravity is still acting on you, but it wants you to go back up. So now, it has to apply a normal force, a greater normal force. That makes your apparent weight now not 0, but if it's greater than gravity, now that's when we start getting into G forces. If it's 2G, that means this is twice as big as gravity. And that all depends on how fast does it have to go, what is the radius of that circle, stuff like that. Does that make sense? Okay? But, and this, Rachel, this is no different than you at the bottom of the first hill of a roller coaster. Same exact thing, right? Gravity's trying to pull you this way, but you're trying to go straight, and the roller coaster wants to make you go up. That normal force has to be big. Because when you go through the bottom of that first hill of the roller coaster, right, you have that, like, you know, it's pushing you down into the seat, okay? But then, right, if you go on an upside down roller coaster, right, now the plane's up here, right?
Planes shouldn't do that.
Planes shouldn't do that, but, I mean, stunt planes do that. Okay. Now, if you're trying to do this, right, gravity's helping out. Does the normal force have to be as big anymore? No. So now your apparent weight is somewhere between 0 and 1G. Does that make sense? Okay. Here you go.
Yeah, I think if you're on top, there's no normal force. If you're on the bottom, you're in.
How about it might not have to be no normal force, but it's usually reduced normal force. Okay? If it's at the bottom, now how big is your normal force? If it was equal to gravity, would you go back up? No. So it has to be what? Yes, in relation to gravity, does it have to be bigger than gravity or smaller than gravity? If it's at the bottom, it's got to be bigger because it's got to push you back up. Does that make sense? Okay. So, Mark, getting back to your question from earlier, this, anywhere else on the circle, it becomes pretty complicated. But at the top or the bottom, the top, you're going to feel the least normal force, your apparent weight is smallest. On the bottom, more normal force, your apparent weight is the greatest. Okay? Does that make sense? So that's how this relates back to the circle stuff. We're messing around with the normal force, and that messing around with the normal force creates that sensation of either being heavier or being lighter. Okay? So on that problem set, number 1, we did a problem where the string was up at the top, and a problem where the string was down at the bottom. The string is playing the role of normal force in this problem. All right, good there? Questions? Other questions? Yes, Tim?
So at the space station, like
Yeah.
in the middle,
Yep.
like, it would be a lot heavier, right?
Say again?
If you're closer to the center, it would feel a lot heavier. Because the radius is smaller. So you divide it by
Except, that's a good question. Okay? So, I mean, that's a really good question. So,
Oh, but your speed is different.
yeah, your speed's different, right? So here, you got this green guy, right? He's going around in the circle as well, right? If we go back to this equation, right? Okay. What has to be true about T for both red and green guy?
Times time's the same.
Time has to be the same, because they all have to make one circle in the same amount of time. But r is shorter, so the speed is smaller.
So are they exactly the same, or does it still change?
Exactly the same.
So you just like stack rooms on top?
Because here, if you do this, that's what this problem turns into, right? Yeah, here. Does that make sense what I just did right there? Yeah. Because if you want it to feel like Earth, what do you want normal force to be?
Okay, but because like the v squared, that doesn't change anything?
Both of these change. Both v and r change.
But do they change at like the same rate?
Yeah. Because they both depend on r. You know what I'm saying?
Yeah.
Okay. So another thing too. This is how
So
you would set up this equation, right?
Yeah.
What happens to m in this equation?
Right, and could you insert the square of the v, and then insert that and
Yep. Yeah. So moral of the story too is it doesn't matter who's on the space station. It could be super big fat guy, or it could be a hamster in the hamster wheel, right? It wouldn't make a difference on what they felt like. They would all feel like they do just here on Earth. Okay. Good there? This is a good chapter. Lots of good like discussion points like this. So. All right. So for tomorrow, right? Note card. This will be your last grade for this grading period. I will get them graded in time for you to do corrections, so you can get those corrections in. Hopefully get them done, by Thursday, so I can get them graded and get them into your grades. That's about it. See me tomorrow morning after school today, 10th period, down in the library. Any of those places would work. All right. Questions? Let me know.